right, today we're taking a look at question 4 for recitation 8. And it's we're trying to find the field as a function of the radius, either inside or outside the bounds, the radius of a spherical volume with a specific charge density. All right, so since it's spherical, we know it's going to have a spherical symmetry. So if this is our sphere here, we're just going to be creating our Gaussian surface either inside if the r is smaller than this big R, or outside if we're looking at a radius that's bigger than the radius of this sphere. So for any Gaussian surface, we're going to have our flux is equal to our Q enclosed over our epsilon naught. And then from there, since it's spherical, we can say that the flux, because again, that's just going to be for any surface, it's going to be the electric field at a point times the surface area of a sphere, which is going to be 4 pi r squared. And that's going to give us that. And then we can set these equal to each other to get that our Q enclosed over epsilon naught equals our electric field at a point times 4 pi r squared for solving for this electric field. So that's going to give us that our electric field at a point with our spherical symmetry. That's our Q enclosed divided by 4 pi epsilon naught r squared. This should also look familiar because if we're looking for the electric field at a point, that's just going to look like if I take this 4 pi e naught, 4 pi epsilon naught, and that's just times the charge over r squared. This is just our equation for an electric field from a point charge. So that's going to have that same spherical symmetry. Now we're going to look at the equation given for our charge per unit volume, or our charge density, which was just some constant alpha times r squared. So if we have our charge per unit volume, it's coulombs per meters cubed, we're trying to find the charge, we're trying to find the enclosed charge in total, so we're going to have to multiply by our volume. But our density is changing as our radius is. So we're going to have our volume of a sphere, because again it's still spherical, it's going to be 4/3 pi r cubed, but we have to do something else here, which is fun and calculus-y, to actually find the enclosed charge, because again, the density isn't constant throughout the sphere. So what we're going to do is at each of our chunks of radius, like a radius here, it's going to have a certain density and it's going to have a certain volume. So our volume of, like, say this is just a sphere, it's going to have a radius to what is actually supposed to be our radius, because again, these are going to be infinitely close together, because this is going to be our dr, which is approaching 0, and that's some radius, which is just going to be our r. So now we're just going to find the volume of that. So that's going to be our d volume for our infinitely small volume is going to be just the derivative of this. So power rule, we're going to multiply by 3, so it's going to be 4 pi r squared, which is just the equation for the surface area of a sphere, which makes sense because when we're taking these infinite pieces, it's going to end up just being this kind of shell, because the dr, what gives it its depth, is approaching 0. So it's going to kind of be, that's also multiplied by dr, sorry. So the surface area times dr, that's what's going to give us our volume, our infinitely small volume. So now what we're going to do is we're going to multiply, at every radius r, we're going to multiply our rho, our charge density, times this d volume, and we're going to sum up all of those different values. And we're going to do this from when our radius equals 0 to when our radius equals r, because that's going to be the total charge of this sphere, is when the radius goes from 0 to r, because again, this is the big R. Big R is just the radius of the sphere, so that's the most charge that we're going to have. So we're integrating from r equals 0 to r equals big radius of our rho times our change in volume, right? So now we can plug in from our equations over here. That's going to be the integral from r equals 0 to r of this alpha r squared, and then again our dv is 4 pi r squared dr. All right, now to evaluate this integral, I'm just going to pull out all of the constants. So this alpha is a constant, and 4 pi is a constant. So then we're taking the integral from r equals 0 to big R of r squared times r squared. It's just going to be r to the 4th dr. And then integrating, that's just going to be our reverse power rule. So that's, again, alpha 4 pi is that constant. We're going to divide by 5, and it's going to be r to the 5th. And again, because that's that exponent, taking the derivative of that exponent would have been multiplied in to get rid of that 5, which is why it's not seen in the original. And we're still evaluating that from r equals 0 to r. Now if we plug in for r, that's going to give us this alpha 4 pi over 5 times our big R to the 5th minus 0. So our equation for the charge is just going to be alpha 4 pi r to the 5th over 5. So then this is going to be our total charge of the entire sphere. So when our radius, when our r is greater than the radius of the sphere, the entire sphere is going to be our enclosed charge. So that's going to give us our enclosed charge if r, little r, is greater than big R. Our Q enclosed is going to be this alpha 4 pi big R to the 5th all over 5. So then if we go back to our original equation up here for our electric field at a point, we have this Q enclosed. And again, this is our Q enclosed when R is greater than our big R. And so that's going to be our alpha 4 pi r to the 5th all over 5. So Q enclosed, that's divided by that 4 pi and epsilon naught r squared. Divided by our 4 pi epsilon naught r squared. And our 4 pi is going to cancel out. And then this is going to simplify to alpha r to the 5th over 5 epsilon naught r squared. But again, that's when just when our little r is greater than this big R. When our little r is less than this big R, we can only include the part of the charge, the part of the sphere that's inside of this smaller radius. So instead of taking the integral from 0 to big R, we're just going to take the integral from 0 to this little r. So for that, our Q enclosed is going to equal the integral from 0 to little r of rho dv. And that's, again, it's going to have the same formula because it's going to have the same density charge, the same volume. It's just going to be evaluated between two different points. So it's going to come out to look approximately the same, but we're just going to plug in differently. So that's going to be this same integral just evaluated at different points. So that's going to end up being our alpha 4 pi over 5 times r to the 5th, evaluated from r equals 0 to little r. And when we plug that in, alpha 4 pi over 5 r to the 5th minus 0, which is obviously just simplifies out to alpha 4 pi over 5 r to the 5th again. But again, this is just our Q enclosed. We still have to divide it by this 4 pi epsilon naught r squared to get our electric field at that point. So it's going to be our alpha 4 pi r to the 5th all over 5, because again, that's our Q enclosed. That divided by 4 pi epsilon naught r squared. And for this one, our 4 pi, again, is going to cancel top and bottom. And we're also going to be able to cancel out some of this r squared, so it's going to end up being r to the 3rd. So that's going to end up being alpha r to the 3rd over 5 epsilon naught. And that's going to be our electric field. That's electric field at that point if R is less than R. So we have our electric field if R is greater than R, and our electric field is if R is less than R, which again, big R and small r. And that's going to give us our equations here. So when it's inside, when R is less than this big R, it's alpha R cubed over 5 epsilon naught. Here's our alpha R cubed over 5 epsilon naught. And when it's outside, R is greater than big R. That's our alpha R to the big R to the 5th over 5 epsilon naught R squared. That's our alpha big R to the 5th over our 5 epsilon naught R squared. Thank you guys again so much for watching. I know this one was a bit of a confusing one, so let me know if you have any more questions or if you want anything else, any other problems explained, and I'll do my best to explain them because I guess Sydney explains stuff.